Not yet. Not yet. Will you? I am behind the curve on the assignment grading. Are you expecting something? Okay. I mean, do the third assignment well. So we were, where were we? We were discussing, I think, the need for understanding, I mean, the role of transmission lines in actual systems. And the last thing that we motivated was, if we limit ourselves to an analysis with respect to only Z parameters, Y parameters, then we have a problem because as we saw, so these Y parameters or Z parameters, they're effective if you can short or open a particular port effectively, right? So you, in principle, you'll never be able to short or open ideally. That is one problem, because even an ideal metal wire will have some inductance, or even an ideal short circuit will ideal open circuit, which probably terminates to something, will have some capacitance associated with it, which essentially means that you can neither effectively short or effectively open anything. The bigger problem was, we saw that when you want to characterize your device, it's called device under test, or DUT. When you want to characterize your device, then you have to connect some source. You have to connect the source and the device through a cable. And the cable will have some finite length, which means that the signal will take some time to flow. And when we say some time, signal always takes some time to flow. But when I say time in this regard, I am saying that the time is a significant portion of the time period of the signal, right? So if it becomes significant portion of the time period of the signal, and if you are not careful and you open up one port or short one port, it is quite possible that because of the reflection, the actual device might not be seeing an open circuit or a short circuit. It might be a combination of both. Even worse, if it's a high power device, there can be a lot of, due to the reflection, there can be a lot of signal swing, which can break the circuit, or there can be oscillations, because your no device is unilateral, right? Because there is always some feedback from associated unintended feedback from the output to input, because of maybe some parasitic capacitance, some parasitic route. So because of that, you can have an exaggerated version of the output getting fed back to the input, depending upon how much swing you have and so on, right? So hence this characterizing a device based on the traditional Z parameters and Y parameters was not feasible. So what people figured was, we understand that if we model currents and voltages in terms of waves, signal waves, then we have a way of mitigating the reflection, right? We have a way of mitigating the reflection, and the way of mitigating the reflection is to ensure that there is always a matched termination at the source side and at the load side. If there is a matched termination at the source side and the load side, there is no reflection. If there is no reflection, there is no, I mean, these problems that come because of reflections will not be there, right? So hence a new set of parameters were envisaged, and they were called scattering parameters, or S parameters. I'm sure you have done S parameter analysis in your UG level courses, but we'll not get into the detail of S parameter analysis. The part that I would like to motivate is how you should start thinking about dealing with circuits at RF frequencies, right? And you should be comfortable in doing S parameter analysis to extract the corresponding impedances or let's say the corresponding Z parameters of a device. Okay, so let's start. I mean, we already had 1 or 2 lectures on transmission lines and matching at the beginning of the course. So we'll start from there, and maybe half of today's lecture will be to motivate why and how we can use the same concepts to uh, to design, okay, or analyze. Fine. So let's start. So let's say I have a voltage source with associated resistance Rs. And let's say I have a load which is also equal to Rs. And if you want to put a transmission line here, that is also fine. And let's say that Z0 is also equal to Rs. Okay. So clearly there is no reflection anywhere. Signal flows through. So now when we talk about signal flowing through or voltage flowing through or current flowing through, the underlying assumption is that we are always talking about power, right? So we are talking about a power in and power out. So when we say that there is no reflection anywhere, we are essentially talking about there is no power reflection. Okay, so now that might seem a bit weird to start off, but hopefully in another 10-20 minutes, it will become clearer why we talk about power. Okay, so we understand that under matched condition, right? Under the matched condition, this is essentially V in by 2. So if I have to find out what is power in, how should I go about finding out the power in? Pardon? Yeah, right. So ultimately here I know that there's no reflection. I can basically find out the voltages at any point. Whatever goes in divides, square divided by R. The naught is essentially the power, right? So your P in is essentially P in squared by RS or 2 RS now, depending upon whether you are taking the amplitude or RMS, right? So if I take RMS, this becomes V in squared by RS, right? Right, V in squared by 4 RS, sorry, because this is V in by 2. And what is the power delivered to the load? What is the power delivered? It will be same because under matched condition, there is reflection is 0. Correct? Under matched conditions, reflection is 0. So power reflected is equal to 0. Therefore, power delivered is equal to P in. Okay. So why am I expressing this in this form? It will become clear if I replace RS with some other load which is not equal to, if I replace the load with some other load which is not equal to RS. Okay, so let's do that. So let's say I have RS and let's say I have RL. Okay, and you can imagine there is a transmission line which is also RL, right? So it's not necessary for this particular analysis, but if you are just wondering, what I'm trying to say is that I'm considering reflection here at this plane. Okay. So once it goes in, let's assume there is no reflection. So if that is the case, I want to find out what is the power delivered in terms of reflection coefficients. Okay, we understand what reflection coefficient is, right? We know that your gamma L is RL minus RS by RL plus RS, right? I want to express the power delivered in terms of reflection coefficient. So we'll do the old school way in which I'll just find out whatever is output power actually using KCL, KVL, and then massage this expression to find out if I can get this power delivered in terms of reflection coefficients or not, right? So power at the load is essentially in this case your V in RL by RS plus RL. This is the voltage times V in by RS plus RL. So essentially this becomes V in squared. Well, square. Now I want to express this in terms of if I want to express this in terms of the power that is going in and power that is reflected, I'll have to take out an expression which is equal to that power going in, right? And if I say that this power going in, so by the way, in this case, if I look at this expression, there is no reflection in the top circuit. So what is the power going in? It's V in squared by 4RS, right? So what I'll do, I will take out this V in squared by 4RS from the expression, in this bottom expression, and then see whatever is remaining. Okay. So essentially means that it becomes okay. So this I know is power in, so I'll just write it in terms of power in. And this becomes, let's say, I say it has to be power in minus something, right? So I'll just say this is P in 1 minus something, right? So what is that something? That I can basically equate the top and the bottom equations to figure out, right? So what will be that something? This is whatever I get essentially is equal to so you get this will become essentially RL plus RS whole squared. It's 4 RL RS. So this essentially is RL minus RS whole squared, or rather RL minus RS by RL plus RS, right? Which by definition is gamma squared. Okay. So I mean, since I have taken all real, it becomes gamma. Ideally, it should be, if I have complex load, it will become mod of gamma. Okay. So essentially your power delivered is the power in 1 minus mod of gamma squared. Mod of gamma if you have real, complex loads. Now, this is something that I'm sure you have seen earlier. So now it might seem like a mathematical trick, right? But there is some physical significance to it. Now, what is the physical significance? Now, what is P in? P in is essentially the amount of power that the source is trying to deliver to the load if there is no reflection, when RL is equal to RS. Okay. So the way I like to think about this is, think of a situation in which I have a V in and I have an RS. And this is also, the load is also matched. Okay. So the power that will be delivered to RS will be equal to this P in. Will be equal to this P in. But it looks like it almost looks like somebody else is pushing out some power from inside the port, right? So if I think from the circuit's perspective, I can maybe model this as RS and maybe some other source which is connected inside the port. right? So why is this useful to model it like this? Because see, I am basically changing these loads from RL to RS. I'm making all the loads matched, right? And I am moving the analysis from an unmatched load to a matched load with a source inside, right? By the way, this will be a control source, obviously, because it's a function of RL and RS, and also a function of V in, right? So what will this be? What will the value of this be? If you basically, if you do the math, if you find out, if you replace this RL, RS and everything and do a Thevenin equivalent, you are going to see this is exactly is equal to RL minus RS by RL plus RS into V. Okay. So intuitively or physically, you can think of this this power going in and power push getting reflected is equivalent to some another source sitting inside the box and trying to push out a power in the opposite direction, right? So that's another way of thinking about how this power reflection works. Okay. Any questions so far? Fine. So the reason this is again useful is sometimes you will see that, yes, the value of the reflected voltage wave will not change, but this is essentially a model, right? So that the way, so if I essentially Thevenize the circuit or rather use superposition, in one case I will see that there is a wave in this side, and if I use the second, I mean the source inside the port, I'll see a wave this side. That's all. It's the same. Yeah. Okay. So that we'll come to that now. We'll come to that now. So his question is, so if I understand your question, what you are essentially saying is that in this configuration, if I have to find out what is the reflected wave, how do I go about finding it, right? So that's essentially the next thing, right? So because when you are doing this analysis, we will not have the time or the bandwidth to break it up and put another source inside. So you have to have a quick way of finding out what is the forward wave, what is the reflected wave, right? So if I use the same model, so when we say forward going wave, by definition of this forward going wave, we are saying that the wave P in is the power that is going into the load, right? So that is without any reflection, right? So by definition, P in is the power going into the load, assuming matched condition. Okay. So if I have a plane here, reference plane here, so what will be the voltage in then? P in is under matched condition. So what is the forward going wave? P in by 2, right? So whatever is the waveform under matched condition should be the forward going wave. Correct? So your V plus will be is equal, that is the plus as in the one that is going into the port is equal to V in over 2, right? So this is why. So this is waveform or voltage under matched condition. Okay. And if I know the forward going wave and I know the total voltage here, I know what is the reflected wave. Now you might say that's a hack. That is a hack, and in cases in which I know the total voltage. If I do not know the total voltage, I have another way of figuring out. I should know the input impedance, right? Then I know the reflection coefficient. From the reflection coefficient, I can find out, right? So what is the reflection coefficient? Here it will be RL plus RS by RL plus RS. So your V minus, that is the waveform that is getting reflected back, will be is equal to gamma L times V plus. Okay, so in this case, this will be RL minus RS by RL plus RS into P in. Right, and when you add these two up, clearly you see that you get RL by RL plus RS into P in, right? So one second. So let me just complete this. VL will be is equal to V plus V minus, that is the forward going wave and the reflected wave, which will be is equal to V in by 2, 1 plus gamma. Yes. I didn't understand. Come again? Yes. Okay. Can you explain why not? I am not getting that question. So are you asking what is match condition? Yes. Yes. Okay, okay. Now I understand Cook's question. He is saying that here we said that power, I mean, V plus is the voltage under match condition, but here I am putting a gamma L, which is for the real unmatched condition. So there seems to be a discrepancy between finding out what is the forward going wave, what is the reflected wave. Yes, good, thanks. So now that is why I did this analysis. So if you look at this, all I have to find out what is P in and what is gamma. What is P in by definition in this analysis? This P in is the voltage that is going in, that is the power that is going in under matched condition, right? So this is what sometimes we can get a bit jumbled up in the mind, because we are basically finding out conditions under, we're doing the analysis of a circuit under different conditions and merging them together, right? So that is done because there is this concept of what is the maximum power that I can draw from the circuit, right? So this maximum power that I can draw from the circuit is P in, right? Or rather, not the source, not the circuit, but from the source. But the maximum power I can draw, the condition is under matched. Otherwise, I'll not be able to draw, right? So if I have to think about voltage going in and voltage getting reflected, then I have to distinguish this under what condition the maximum maximum power gets transferred, right? And then use the actual reflection coefficient to find out what is the reflected wave. Kind of superimposing, but I wouldn't use that term, because superimposing is when you have multiple waveforms in the multiple sources in the same circuit. Here we are essentially changing the circuit itself, right? To come to align with the definition. Okay. So this is similar to saying, by the way, this is no voodoo or anything, right? So in the sense that, let's say we have this, right? So let's say this is R, this is the Z naught is also equal to R. So when we talk about the forward going wave under matched not matched condition, under this condition itself, what is V plus? Vi by 2, right? V in by 2. Why? Because when the wavefront comes at this junction, it has no way to know what is connected at the other end of the transmission line, right? It essentially sees a matched termination, the forward going wave. But after a round trip delay, there will be a reflected waveform, right? But when the wavefront is going in, it has no clue what it is going into, right? So when I do not have a transmission line in this picture, it becomes difficult to appreciate that. But if you want to make that analogy, what you can think of is that there is a small transmission line which doesn't have any delay, right? Negligible delay. of Z naught is equal to RL. Or Z naught, sorry, you can, I should have put it here, right? Where Z naught is equal to RS, right? And you can assume there is another transmission line here where Z naught is equal to RL. And then you do the analysis at that junction. So that way, your that discrepancy of thinking of two circuits getting superimposed will not be there. Okay. Yes. Correct. So his condition, what he is essentially saying is that the condition for maximum power transfer is conjugate match, and matching is RL is equal to ZL is equal to Z. That's a reflection match. ZL is equal to ZS, right? So this condition is for power match. So that's why. Okay, so let me try to answer it in a different way. So this condition is for reflection match, not power match, right? This condition is for reflection match, and if we have to do the right. Come again. If we put Z in equal to Z in star, yes. Mm-hmm. Gamma won't be equal to 0. Gamma won't be equal to 0. Correct. You will be deriving maximum power. Yes, that's true. But that maximum power will not be, okay. So in that case, okay, I understand what the problem is. The maximum power in that case will not be equal to V squared over RS. It will be the real part of basically in that case, when you are saying Z is equal to Zn star, which means you are assuming that the source has a complex load also, complex impedance also. Otherwise, you cannot have a match, right? So in that case, instead of RS, you should have a ZS, and then you redo the analysis, right? But that's a good question. So maybe I do not have an offhand answer to that right now. So I'll think about it and see where the maximum power, where this analysis correlates with the reflection match thing. So I know the answer to that, but I do not want to say it aloud. Let me think about it. Maybe I'll come back in the next class. Okay. Okay, fine. Any other question? Okay. So now that we understand what is this, I mean, for the physical meaning of these reflection coefficients and power match and power reflection and so on, let's move on and formalize the S parameter definition. Okay. So what are we essentially saying? We are essentially saying that if I have a two-port network, and I have a forward-going wave V plus, and I have a reflected wave V minus. And let me now distinguish between the ports, saying that this is V1 plus and this is V1 minus. And this is V2 plus and this is V2 minus. So by the way, be careful with the direction of the arrows with respect to the definition. Okay. So plus means always going into the port. Okay. So if that is the case, what we are saying is that there is a relationship between, obviously, I mean, we are assuming something is connected on port 1, something is connected to port 2, and so on. So if that is the case, then we know that there will be some relationship between these forward-going waves and reflected waves between both ports. So in general, assuming everything is linear, we can basically say V1 minus will be equal to some constant times V1 plus some constant time V2 plus. Similarly, V2 minus will be some constant times V1 plus some constant times V2. Okay. And these constants are essentially the S parameters. And the first constant is S11, this is S12, S21. Now, how do we find out this S11 experimentally? The reason we can find out this S11, I mean, firstly, what is the, again, I'm recapping, what is the necessary of going into this into this set of definitions? It is important because ultimately the goal of going to a different parameter was to ensure there is no reflection, right? Which essentially means that I have to find out a condition in which your V1 minus and V2 minus can go to 0. If there is no reflection, there's no problem, right? So under what condition then, let's assume V1 minus can go to 0. So if I have to ensure that V1 minus goes to 0, what do I need to ensure? Pardon? If I have to ensure that V1 minus goes to 0, oh, sorry, I mean, let's do the output side first. If I have to ensure that, so let's say, let me put a load here, right? So I have a transmission line and I have a load. RL, some Z0, some Z0. Okay, and Z0 and has some time delay tau d. Without time delay, it's not a problem, right? So now from the from the perspective of our, let's say this 2-port we want to characterize. Okay, if we want to characterize this 2-port effectively, what do I need to ensure at the output side? We want the reflection to go to 0, but which reflection do we want to go to 0? Yeah, so my question is, do we want V2 plus to go to 0 or V2 minus to go to 0? We would want V2 plus to go to 0, right? So V2 plus 0 means that there is no reflection from the load end, right? These again, the distinction is this plus minus V1, V2 plus minus are with regards to the 2-port network, not with respect to the load or the source. But if we want to ensure that we want the reflection to go to 0 at the load end, we have to ensure that V2 plus should go to 0, right? So fine. So if we want V2 plus to go to 0, what do we need to ensure? That RL is equal to essentially, and basically the output side is matched, right? So what do we need to ensure that output side is matched? So we have to ensure that so again, the thing is, we were assuming everything has come from practical considerations. We are assuming that your long cable starts right at the 2-port, right? It's basically the length of the cable that's the problem, right? So we are assuming that the cable starts right at the 2-port, which essentially means that we have to ensure that there is no deflection from the load after the signal has gone to the load. So which essentially means that we have to ensure RL is equal to Z0. If RL is equal to Z0, then there is no long reflection that comes back. There can be reflection at this. That's fine. Because why that's fine? If that length is infinitesimally small with respect to the wave, with respect to the time period of the waveform, then essentially that is equivalent to saying your load is directly connected there, right? If the load is directly connected there, then it's not a problem. The problem comes because it has to come through a round trip delay. you are basically, by ensuring that your RL is equal to Z0, you are negating that round trip delay, right? So if you ensure that RL is equal to Z0, so this you can do because RL is sitting outside the box. Okay. If you ensure RL is equal to Z0, then V2 plus goes to 0. Then your V2 minus, it becomes S21 times V1 plus, or in other words, the definition of S21 is V2 minus by V1 plus under output matched condition. Okay. Yes. We haven't talked about input side as of now, but what's the point? Okay. You will be able to determine that's the value of will be 0, right? If input is matched, there is no reflection at the input. Your okay, fine. So no, what do you want to determine, right? So, for example, if I am trying to understand your question, you are trying to figure out the S parameter. You are trying to figure out this individual S11, S12, S2, and S22. No. This is only one condition in which, under this condition, you are able to find out S21. This condition might not be equivalent of, might not be the same for finding out S11. For example, when you are doing Z parameter analysis, at times you are opening the output port, or at times you are opening the input port, and are doing different types of analysis for each condition. Similarly, here you will have to sometimes sometimes match the output port, sometimes match the input port, depending upon what you want to find out. Right? So, for example, I mean, if you look at, if I take your Q, let's say I want to find out S11, right? From this equation, I need to isolate S11, which means that I have to ensure that S12 doesn't play a role at all. Correct? If I have to isolate S11, and I do not want S12 to play any role, I have to ensure that V2 plus goes to 0. Right? So how do I ensure V2 plus goes to 0? By putting an output match. So I put an output match, find out the ratio of the input waveform, the reflected waveform to the forward going wave. That ratio gives my S11. Right? Okay. So that's how you do. Basically, you just like you do Z parameter or Y parameter analysis, you open or short individual ports. In this case, you match which port you want, right? So just to continue to finish up the discussion that Andrew was alluding to. So to find, let's say, S11, ensure V2 plus is 0. So how do you ensure V2 plus is 0? Your output is matched. So then under that condition, S11 is equal to V1 minus by V1 plus. Okay. Similarly, you find out S12 and S2. Similarly, you find out S12 and S22. But again, the key thing is that these definitions are valid only when either of these two ports are matched. Okay. Fine. So even though this is obvious, but hopefully the next discussion will kind of conclude the importance of S parameters. and why S parameters are, I mean, if you are not careful, what can go wrong? So let's say so these scattering parameter analyses are done by a big box. It's called a vector network analyzer, right? If you go to the lab, you'll see a big bulky box sitting there. It has 2 ports. So it will have 2 ports, big screen, bunch of switches. And what you do, these are long cables, and you put your device under test here, right? So I should not have drawn it like this. It looks like these 2 are ports. So you assume that there is a return path here, and assume that there is a return path here. Okay. So you have these big long cables, and let's say you want to characterize this this guy, this 2 port, and let's say I want to characterize only one resistor, just a resistor. Find out the impedance of the resistor using this S parameter analysis. Okay. So what does this 2 port? I mean, then I don't need the second port essentially, right? So all I can say is that it's a 1 port analysis. I can say that I want to find out the impedance of this RL. Okay. So what we are doing is trying to find out the impedance of the RL. And this is my setup. Now this is the long line. Okay, which means it has a round trip delay. Okay. So when it has a round trip delay, and let's say I have looking at here, right? Now to ease calculations, I'm just assuming this guy is matched to RL, but it need not necessarily be the case. In fact, it's not the case. It's not normally matched to RS, but I mean, you will get the same kind of intuition, but with a slightly messier result. But let's assume that this is equal to RL, just to motivate as to why this is this can be an issue. So what is V1 plus? This is again under matched condition, which is equal to V in by Vi by 2, right? What is the reflected wave? The reflected wave is now, so this guy, okay, no, I think I messed up. Okay, sorry. So let's do the one that is actually the condition. Sorry for this back and forth. So let's assume this Z0 is equal to RS, which is actually the case. So what is the reflected wave now? The reflected wave is this guy goes all the way, comes back. The reflection happens at this node, and this is equal to the forward going wave here is Vi by 2 e power minus j omega tau d, where tau d is the delay of the line. So this is tau d is the delay of the line, right? So the reflected wave is essentially the reflected wave at this junction is gamma L times Vi by 2 to the power minus j omega tau d. And the reflected wave that comes here is gamma L Vi by 2 e to the power minus 2 j omega tau d. Right? So what is your S11? By definition, S11 is reflected by incident, which is equal to gamma L e to the power minus 2j, right? And gamma L by definition is RL minus RS by RL plus RS times e to the power minus j2 omega tau d, right? So if we are not careful with the delay of the line, right? If you're not careful with the delay of the line, and you say that, okay, I have only a resistive load associated with it, all I will do is I'll take whatever S11 I have, because ultimately you are observing everything at this plane, right? So what I will do is, I know that the impedance looking here, let's say is Z in, at that plane, looking into at that plane, impedance is Zin. So your gamma at the source side is equal to Zin minus Rs by Zin plus Rs, right? And I am going to find out Zin from my observed gamma at that end, right? Now gamma at the source side is essentially S11. So this is equal to S11. Now, can you comment on if I find out if I assume that Zin is equal to the actual value of the resistor, right? I'm trying to find out, I'm trying to characterize the value of the resistor using S11. If I assume that Zin is equal to the value of the resistor, will I get a real impedance or will I get a complex impedance? What I'm trying to say here is that from here, if what is Zin? Zin in this case will be essentially Zin over Rs will be 1 minus S11 by 1 plus S11, right? So this times Rs. So this Zin, is this a complex quantity or a real quantity? It's a complex quantity. Now, if I am not careful, why is this complex quantity coming? Because I have this long line, right? So what I am saying is that in the lab, I have only connected a metal wire, which is supposed to have zero impedance, right? Connected a load at the other side of the metal wire. And I'm trying to find out the impedance looking at this side of the metal wire, right? I know that S11 is reflection coefficient, this minus that by this plus that. I find out Z11 and I suddenly get a complex imaginary impedance, right? So even though there is apparently no capacitor, no inductor, only a long metal line and a purely resistive impedance, a resistive load, I am still getting a Zin, right, which is imaginary, right, or rather has an imaginary term. So if I simply do this, if I simply find out S11 at the source side and do this 1 minus S11 by 1 plus S11, you are going to get an error. And what is the root cause of the error? The root cause of the error is a round trip delay. So how do you get rid of that round trip delay? You will have to understand a priori what is the round trip delay, then multiply the S11 with that inverse of that round trip delay. Basically, if I multiply S11 by e to the power j2 omega tau t, then that round trip delay goes off. Then I do this Zin calculation, I am going to get exact value of RL. Okay. So now this process of de-embedding these effects is called calibration. So this is only for one port. Similarly, you can do for the other port to find out, to de-embed the effect of these delays. Now, this is useful in case of these instruments, is because you see that these instruments come up with long wires which are connected to the instrument. You cannot take it out, because when you calibrate, it already knows to some extent what is the delay of that built-in wire that has come in. And if you want to add something to it, right, your DUT device under test need not necessarily be connected just where the wire ends. Some elongated wire can still be there. So you'll have to connect and then run a calibration cycle. This calibration cycle is essentially telling the PNA is that, hey, I have connected some things now. Now you recalibrate your whatever you think is the amount of delay this set of wires are giving you. So it is going to send you a test signal and then see when it comes back. From there, it is going to find out these calibration effective amount of tau Ds in this case, and then it will recalibrate. And before giving you the impedance, it gives you the effective Z11 and everything also. Before giving you the impedance, it will do this multiplication itself and give you the exact value. If you do not do that, right? If you do not do that, you are going to see that even if you have a resistive impedance, you are going to get complex values. Okay, so that is something to keep in mind. Yes. Okay, good question. So its question is, what is a two-port here? I didn't take anything into account. This is a one-port network. This is not a two-port. If nothing is connected this side, right, you can assume that. So I say This is your generic 2-port. You assume that this is 0, this is 0, this is 0. Then it doesn't matter whatever you connect here. It's not going to affect the input side. Here, yeah. Ideally here, but you cannot take it here because you cannot connect the device just at the wherever the VNA ends or begins. So you need, obviously you need that long wire. The whole purpose of generating this S11 framework was because you cannot do away with that long wire. If I could have done away with the long wire, I would have directly done Z parameters or Y parameters. S11 was not, S parameters was not required. Yeah, yeah. Anything with 2 is not of concern. Yeah. Yes, only S11 is of concern then. So the reason I showed this is because often you are trying to find out the input impedance. In that case, it's fine. You can still do it, right? Yes. Yes, correct. Right. So moment you have anything that is long enough, by long enough, I mean, it should be significant fraction of the time period of the delay associated with that wire should be a significant fraction of the time period of the signal. Then you'll have to account for this round trip delay and you have to multiply, right? It's a good exercise. You can, I mean, sometimes you can go to the lab and see, right? Just connect one simple resistor, you are going to see all sorts of circles and imaginary parts and all. And you can do this approximate hand calculation to figure out what is the speed of the light and do this e power j to 2 omega tau d, and you see that the effect of that comes down. But obviously the VNA does it better automatically if you ask it to do it with using its internal algorithm. Okay, fine. How much time do we have? 15 minutes, right? Yeah, okay. Fine. So this is as far as I wanted to talk about S parameters. Another reason I wanted to talk about S parameters is because in the assignment that is there, you will see that I have talked about using S parameters analysis to find impedance. So that is useful. I mean, you can do the analysis the old school way also, because in simulation, you don't need to bother about these long wires. You can basically connect impedances directly and find out. It's going to give you correct results. There's no two ways about it. But obviously, it becomes sometimes clumsy to change test benches, find out apply V, find out R, D ratio and all. So there's a good S parameter analysis built into the software, right? So if you use SP analysis and you run SP, that is going to give you the impedances also, Z11, Y11, everything it will plot. So just that you have to ensure that you are doing the right thing, right? So as long as you do that, it should be fine. So that is one of the reasons I wanted to talk about this. Another thing that you can do, it's not a part of the assignment, is to see what happens. I mean, you can model the effects that we have talked about in the class with a long line, right? Just put a transmission line of like arbitrary length in simulation, and then see what happens to these to the impedances or to the voltage swings, or even for that matter to the stability of a circuit or not, right? So I mean, you can take one of the stable circuits that you might have designed in a 610 or 613, put long transmission lines and open circuit output side and see what. Okay. So now, till now in this course, we started off with overview of RF systems, right? Very high level overview we covered. Then we covered noise analysis. We covered matching, right? To some extent, noise we covered into some detail. The part that we have not talked about formally as of now is distortion. We have talked about the effect of distortion hand-wavingly and say that output amplifiers can get saturated if the signals are very high and so on. But there are ways of, obviously there are ways of characterizing those distortion, right? So that is what we are going to talk about next, right? And that will complete all the important parameters that are necessary to design for in an RF system, right? And then we are going to look into the LNA and then mixer and then a PA, right? So that's the plan as of now. So let's talk about distortion. So intuitively, we all have a feel of what distortion is. That is, if you apply, if you have a voltage, so if you have any amplifier, which is, you have any amplifier which is operating with some finite voltage source, finite rails, then obviously, if your input goes beyond the rails, the output will not be able to track. It will get clipped, clamped, and all those things will happen. If the output is not a linear function of the input, then obviously there is nonlinearity, which means distortion, right? So that is a very hand-wavy and way of characterizing what distortion is. But obviously, we are not interested in giving an input so high that it kind of gets clipped, right? So we like to give inputs which are which will ensure that your system works moderately linearly, right? But we understand that nothing will be fully linear. There will be some additional distortion components associated with it. We would like to characterize, we would like to find out those distortion components, right? So we are essentially talking about weak nonlinearity, right? So weakly nonlinear circuits. Okay. So now again, graphically, what does it mean? So if I characterize an amplifier with, let's say, V in and V out, okay. So I'm sure you have seen this graph multiple times. You will see that something that goes like this, right? So what does this mean? These two edges, what do they signify? Where V out is flat parallel to the x-axis. Yeah, right. So for amplifier is getting saturated because for any incremental change in V in, there is no change in output, no change in V out, right? So output is not responding, amplifier is getting saturated. Somewhere over here, clearly there for some change in V in, there seems to be a kind of linear change of output. And the ratio of that change of output by change of input is essentially your gain, right? So, so that's the amplification factor. But however, since everything is made out of nonlinear devices, it's never going to be fully linear. We have some amount of curvature in that linear plot also, right? And that gives rise to distortion. Okay, so that's what we are going to talk about here. So we are not working here. We are still working around here. Okay. So the reason this is important is that we are going to neglect many of the terms later on, and that you can neglect them. Sometimes you can neglect them because if you have higher order terms, if they are non-nominal. So it will become clear in the next few minutes. So this is as far as what we are trying to do is concerned, and how we are going to do is what we are going to do talk about next. So in general, we are talking about the effect of this distortion in on periodic signals, right? We are talking about the case in which, let's say I have a sinusoidal input. We are talking about narrowband systems. We have assumed that we have a sinusoidal input, and if I pass it through a distorted two-port, what are its effects? Okay, so if I take again the simplest of examples, so let's say, so this is the amplifier, and this is the characteristics. Around this V out V in equal around the origin, I can express this V out to be equal to some Taylor series expansion of of this curve around the origin, which means I am going to get the way I have drawn, there is no DC component, but let's assume there is a DC component, right? So let's assume there is some VDC plus A1 V in plus A2 V in squared plus A3 V in cube plus dot dot dot. Okay. So further, the assumption is if I do a Taylor series expansion, these V ins are incremental V ins, right? Around the operating point, right? So this V in not, I shouldn't say VDC here because that is the output. I should say around operating point. So if the input is, let's say, VP sine omega t, let's say the cosine omega t, what will your output be? Your V out will have, clearly I will have a DC term, which is VDC. Then I'm going to have a component at omega, right? At omega, the component will be A1 times VP cosine omega t, right? Where A1 is essentially the kind of the fundamental gain of the amplifier. Then what will be the effect of this guy? A2 V in square. Right. So yeah, so essentially I'm going to get this. If I expand that term, I'm going to get A2 VP squared cos squared omega t, which means A2 by 2 VP squared 1 plus cosine 2 omega t. Okay. So this extra DC term is going to get added up here. And the other term will contribute to 2 omega, which is A2 by 2 VP squared. Right? And what will be the effect of this guy? A3 V in cube. It is going to give two terms, right? At 3 omega and at omega, right? So you are going to get, so A3B in cube is essentially so this is A3BP cube by 4. 3. So what was the thing? Cos 3 theta is 3 cosine theta plus 4 cos cube theta, right? So it's become by 4, 3 cosine omega t plus cosine 3 omega t. Right? So essentially, again, so this term contributes here, and at 3 omega, you get a 3 Vp cubed by 4 cosine 3 omega t. Okay, so one way to characterize your distortion clearly is to find out the components at omega, 2 omega, 3 omega, and whatever other omegas you have, right? So the one that we measure is the component at omega, The one that we do not want are the components at any other frequencies, right? Forget about the DC, because DC I can filter out easily. So you just put a capacitor in series and high pass filter, it will go off. So we do not bother about DC. But if I find out the power associated with each of the other terms other than omega, they give the harmonic distortion power, right? This is for harmonics because you have multiple, you do not have like a fractional frequency component here, right? You have omega, then you have 2 omega, 3 omega, and so on. So these are harmonic frequencies. The power associated with the harmonic frequencies are the ones that we do not desire. Okay. So naturally, what you need to do is, firstly, you should do your best to ensure that the coefficients A2, A3, and all are minimal with respect to A1, right? Again, I shouldn't say that, because what is the when I have expressed A1, A2, A3 in the top definition, what is the unit of A1, A2, A3? What is the unit of A1? It's unitless. What will be the unit of A2? It will not be unitless, right? It will be volt inverse, right? Similarly, A3 is volt inverse squared. So if the circuit is weakly nonlinear, which essentially means that by definition, we expect this guy to be more than A2 V in squared plus A3 V in cube. That's the assumption, that's the definition of a weakly nonlinear circuit. Now, for that to happen, clearly you cannot have this assumption valid for all values of V in, right? Because V in is a stronger function. V in cube will be stronger for larger values of V in than for smaller values of V in, right? So under what assumption, let's say I take this A1 V in plus A2 V in squared, these two terms. So under what condition, there is a condition for V in for which the weakly nonlinear assumption is valid. And what is that condition? You have to ensure that A1 V in is much greater than A2 V in squared, which means that V in has to be much lesser than A1 by A2, right? Which essentially means that limits how far you can go from the operating point, right? If you go too far, then you are essentially saying a V in is very large. Okay, similarly, we will have a constraint if you want to impose that same condition for A3 V in cube. Okay, so the reason that is important is because if we are working under those assumptions, then clearly I can probably neglect this term with respect to this term. Similarly, I can neglect all the other folding back terms. Basically, you are having this bunch of extra terms. I can neglect all those bunch of extra terms and keep the dominant one under any other DC omega 2 omega 3 omega, right? I can keep only the dominant term. Okay, fine. So now this is the easy way to characterize any system. But the issue is we are talking about narrowband systems here, right? So till now, whatever we have talked about your signals are within some narrow frequency range around some local oscillator frequency, right? So maybe around 1 gigahertz, you have a range of couple of megahertz and so on, right? So here omega is, let's say, 1 gigahertz, right? 1 gigaradian per second, let's say. So your 2 omega will clearly be 2 gigaradian per second. That anyway is out of band, right? You have a filter which is going to filter it out. Then why do I care? Does that make sense? What we are saying is that I have a sinusoidal input. I pass it through a nonlinearity. It is going to create a fundamental which is at omega, which I want. But looks like the 2 omega is like out of band. It's going to 2 gig, where anyway I do not have any activity, right? I have an narrow band filter, I have an LC filter, it is going to filter it out, right? So then should we care or should we not care? We should care, because while doing this analysis, I assume that I have a single tone. That did not necessarily be the case. In fact, that is never the case, because a single tone doesn't have any information, right? Almost always you are going to have multiple tones and you don't know what the tones will be around that center frequency. Right? Maybe you have some signal at 1 gig, maybe you have another signal at 1 gig plus 1 megahertz. Right? So what's the effect of those tones when they are closely spaced y, right? So an example is, let's say, instead of taking a single tone, I'll just show you one example. So let's say at so your tone is, let's say you have two tones. Let's say V in is equal to Vp cosine omega 1t Vp cosine omega 2t, where let's say omega 1 is 1 giga radian per second and omega 2 is 1 gig plus 10 meg radian per second, right? Close by. So what's going to happen? Your A1 VP, I mean, the term at omega is fine, right? The fundamental is fine. I mean, that's what we want. Let's concentrate on the cubic term. So what's going to happen to the cubic term? So if I expand this, I am going to have Vp cosine cube omega 1 plus Vp cube cosine cube omega 2, right? Then I am going to have some cross product terms. What are the two cross product terms? The cross product terms will be 3 Vp squared cosine cosine squared omega 1t times Vp cosine omega 2t. And then I'll have the other one, that is Vp cosine omega 1t times Vp squared cosine squared omega 2t. Right? These are the two terms. Now, these terms are important because if I expand this, so this will give me 2 omega 1, and this is omega 2, and the 2 omega 1 and 2 omega 2 are multiplied with each other, which means I can further trigonometric identity, I can break it up as 2 omega 1 plus omega 2 and 2 omega 1 minus omega 2. So what is happening at 2 omega 1 minus omega 2? So what is that value? 2 omega 1 is 2 gig minus 2 gig plus 20 meg, which means you are getting something at, 1 gig plus 10 meg, right? 1 gig plus 10 meg, which means you are getting something at 1 gig minus 10 meg. Right? Now, this is in your band. Right? This is not at 2 gig. Right? This is not at 2 gig. This is near exactly where your fundamental frequencies are. Not exactly on top of your fundamental, but nearby. It's only 20 megahertz away or 10 megahertz away from 1 gig. And this is coming not because of fundamental, this is coming because of your distortion component. Right? So in the next class, what we'll see is that what is the effect of this distortion component and how do we characterize it? Okay. So that's another crucial aspect of why RF designs are sometimes the metrics are different, because when you are doing analog design and you want to find out harmonic distortion, you generally tend to put an input. If your, let's say, bandwidth of your amplifier is 10 megahertz, you put a distortion component at 3 megahertz, assuming that the third order will be at 9 megahertz, and you find out the strength of that. That's fine. That is accepted. But if your bandwidth of interest is only very narrow, you cannot do that. Right? You have to find out different ways of characterizing your system. And in RF, that's why we have these matrices that you apply multiple tones close by and then see what folds back within your band of interest. Okay. Okay, fine. Stop it. No. So let's say your signal, you are sending two tones, which is at one is at omega 1, one is at omega 2. Quite possible, right? I am sending two tones because I mean, even our voice components are not monotonous, right? So you'll have multiple tones when you are sending signals, right? So let's say you are hitting a tone at 1 gig. Let's say 1 gig let's say your baseband signal, let's say, is at 1 kilohertz, and the second tone is at, let's say, half a kilohertz. Right? When you are singing, when you are speaking, if you see the spectra, you are going to see all sorts of spectra between 0 to 1 kilohertz or 10 kilohertz or something like that. Now you're up converting them around 1 gigahertz and you're sending it out through your power amplifier. So now your power amplifier is distorted, right? Or when you are receiving a signal, your LNA is distorted. So when you are receiving these pristine signals, let's say when you are receiving these internet signals and you pass it through a distorted component device, you are going to generate these additional tones. And these two tones and these two components are there because you have that cubic nonlinearity down. Right? Because of this cubic nonlinearity, you are seeing an additional tone which was not supposed to be there. The presence of that tone is a testament to the fact that your device is nonlinear. Larger the tone, more the distortion. So that's how we characterize RF systems, by sending multiple tones, because we do not have the option of sending only one tone and just seeing what's going to be its effect, because the harmonic of that tone can become out of band.
That we have a tone at 1 gig minus 10 megahertz, and due to this mixing another tone at 1 gig minus 10 megahertz.
Yes, yes, it can. It can. In fact, that's why there are certain specs. It's called adjacent channel rejection ratio, ACLR, which essentially means that you stay in your lane. Basically, I don't care how nonlinear your device is. Even if I send, let's say I'm designing a power amplifier, and I know that maximum power that I can transfer is 0 dBm. You have to ensure that anything that out of that band, including your distortion components, has to be lower than, let's say, minus 50 dBm or minus 60 dBm. Right? So the next, whatever exactly the point that you were making out, that I should not be infringing upon the next band because my device is nonlinear. Right? So there is a spec for that. That's why. And the reason of that spec is this. Yeah. Okay. Thank you.